Good afternoon, one and all. Today we will going to discuss about the Norton's theorem, AC fundamental and related to its example. In node voltages, the Norton theorem and AC fundamental. After that, the agenda for here, the procedure of node voltages and explanation, the procedure of the Norton theorem and its explanation, and AC fundamental basics. See the procedure of the node voltages and its explanation, and AC fundamental basics. Then what is the nodal analysis? The nodal analysis provides a general procedure for analyzing the circuit using the node voltage as the circuit is the variable. See here, this circuit is able to provided here, and basically in the node voltage, here is the voltage will be generated across the node where the current will be incoming from the other sources and it leaving from the junction. Here is the node 1, 2, these are the 2, 1, 2, 3, there are the 3 nodes, and individually there we have calculated the voltage drop across it, the V1 with respect to the ground. Then the steps to determine the node voltages. The first step is that to determine the number of the nodes within the network. Then to pick the reference node and the label each remaining node with a subscript value of the voltages V1, V2, V3 and so on. Then after we have deciding the node voltages V1, V2, V3 respectively, to apply the Kirchhoff's current law at each node and expect the reference. To solve the resulting equation, for the nodal voltages. Here to solve the resulting equation for the nodal voltages. Then this is the one example. In this example we have find out the V1 and V2. We calculated the value of V1 and V2. Here there are the two current sources available. This current source is in parallel with 5 ohm and 20 ohm respectively, and its node voltages is V1, V2 respectively. Then what we do, applying the KCL at V1, apply the KCL at V1, there is a V1 minus 0 upon 10, it will be V1 upon 10 plus V1 minus V2 upon 5, which is equal to 2, because this is the incoming current, and that incoming current from this node, the current should be divided. That's why we will taking this node, that is the V1 upon 10 plus V1 minus V2 upon 5, which is equal to 2 ampere current. Then we have applied the KCL at node V2 for this. There is a V2 minus V1 upon 5 plus V2 minus 0 upon 20, which is equal to minus 6, which is equal to minus 6, because this current should be, here is the both the current will be away from the node, that's why it is the minus 6. Then the nodal analysis clearing the equation from equation number 1, V1 plus 2V1 minus 2V2, which is equal to 20, therefore 3V1 minus 2V2. From this equation we have calculated. Then we move towards the V1 plus 2V1 minus 2V2, which is equal to 20, therefore V1 minus 2V2, which is equal to 3V1 minus 2V2, which is equal to 20. This is the equation number 3. Then from equation number 2, there is a 4V2 minus 4V1 plus V2, which is equal to minus 120. Therefore minus 4V1 plus 5V2, which is equal to minus 120. This is the equation number 4. Then from equation number 3 and equation number 4, we have calculated the value of V1 and V2 respectively. Therefore V1, which is equal to minus 20 volt, and V2, which is equal to minus 40 volt. Then next, then we move towards the Norton's theorem. Basically in the Thevenin's theorem, what happens in case of the Thevenin's theorem? The Thevenins told that there is whatever the complicated circuit, that complicated circuit is converted into its Thevenin's voltage and Thevenin's resistance, and load resistance is removed at a first step, and finally we connect the load resistance across the node. Therefore the load current, which is equal to Vth upon Rth plus RL. This equation is provided by the Thevenins. But in case of the Nortons, this scientist is Edward Laundry Norton, was an accomplished the Bell Lab engineer and scientist, the famous for developing the concept of the Norton's equivalent circuits. Means here is the source transformation technique is used. Basically, in case of the source transformation technique, the voltage source is converted into the current source, and the current source, how to use the current source, which is told by the Nortons. Then this is the Norton's theorem. The any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of the current source and its parallel resistance. Means here is the current source, which is called as the Norton's current, and whatever the equivalent resistance, which is called as the Norton's equivalent resistance, Rn. Means